In this presentation, we'd like to have a conversation about the law of conservation of momentum. First words that come to mind are, to every action there's always opposed and equal reaction. But would it surprise you to know that that's not the law of conservation of momentum? That's the principle of conservation of momentum. So what's the difference between a principle and a law? A principle is an adopted rule. Synonyms for that are assumption, convention, axiom, or postulate. It's not something that has been proven, it's just something that has been noticed or adopted as a general method for application. Another synonym might be rule of thumb. A law is something very different. We'll use the mathematical definition here. It's a formula that is always true within a given context. It can be analytically proven, and it must always be true, again within that given context. So to dig a little deeper, in 1687, Isaac Newton gave us the principle of conservation of momentum. In 1918, M.E. Noether gave us the law of conservation of momentum. She proved analytically that every continuous symmetry of the action of a physical system with conservative forces has a corresponding conservation law. And the specific example we're interested in is where the Lagrangian exhibits translational symmetry and the conserved quantity is corresponding linear momentum. We can go a little further with that. Not only is linear momentum conserved when the Lagrangian is translationally invariant, momentum is conserved only when the Lagrangian is translationally invariant. And again, this can be proven mathematically. So I'd like to offer that take-home number one in this presentation is momentum is only conserved if the Lagrangian is translationally invariant. What that means is that physics is perfectly comfortable with the idea that momentum need not be conserved. We just need to engineer the Lagrangian with a translational variance and put that into practice. There is one caveat. People are commonly quite uncomfortable with the idea that momentum need not be conserved. In general, we seem to be quite wedded to the idea that conservation of momentum is an inescapable law of physics. We see quite commonly in some of our renowned textbooks that momentum is commonly assumed to be conserved, that the Lagrangian is assumed to be translationally invariant. It's much less common that the case where the Lagrangian is not translationally invariant is treated or discussed. There's a good example here where the author says that when you tamper with the third law, you are placing conservation of momentum in jeopardy, and there is no principle in physics more sacred than that. I would question whether it's appropriate to use the word sacred in a physics textbook, but it certainly is a good illustration that people are commonly quite uncomfortable with the idea that momentum need not be conserved, even though physics has no such limitation. Of course, we need to be quite careful about how we account for momentum and take into account all of the relevant components, including electromagnetic field momentum. So let's talk about the case of transverse momentum of an electron in an electromagnetic wave. In this case, there is an exchange of energy and momentum between the particle and the electromagnetic field. It's interesting to note that in the paper referenced here, things don't quite add up. The author notes that we continue to be puzzled as to why the result is 8/3 times larger than that required to satisfy momentum conservation. Let's just keep that in mind as we move forward. If we look at it on the surface, in this case, there is an exchange between linear mechanical momentum and electromagnetic field momentum. What's happening is we are gaining and losing linear mechanical momentum. We may pick up some linear mechanical momentum as a result of the exchange with the electromagnetic field, but we're forced to give it back when the field reverses. Still in all, that is a very interesting example that we were able to manifest this linear mechanical momentum, even for a very short time. But what we really want is to be able to accumulate this linear mechanical momentum from an interaction with the electromagnetic field. For instance, if we had an electron that could change its charge in sync with the laser, then we would get that little jolt of momentum at each antinode and be able to accumulate it over time. Fortunately, we have the next best thing, the optical forces on an induced dipole, or the case of optical trapping. In this case, the electromagnetic field gradient can give us a force on the particle in question. In the case of optical trapping, the electromagnetic field induces a polarization on the sample at each antinode, forming a transient dipole within the sample. When the dipole forms, it finds itself in an asymmetric electric field, a gradient, and the upper end of the dipole experiences a stronger force than the lower end of the dipole, so the particle is drawn along the field gradient to the area of highest optical intensity. The case is the same for the opposite antinode. The field has reversed, therefore the dipole has reversed, but the gradient has not. And once again, the particle finds itself drawn toward the area of highest optical intensity. So in this case, we've achieved the goal of accumulating monodirectional momentum with each passing antinode of the laser light. And the object experiences a net force due to the optical gradient forces. We have a condition where we are able to accumulate mechanical momentum solely from the electromagnetic field, with no second mass involved. Now this is a very interesting case. We have a force on an object with no transverse force on the laser. If we put an enclosure around the whole thing, we can see that there's a net force on the device with no propellant. That's a bit counterintuitive. We note that this is due to the gradient force. It is not photon momentum. There is no net power flow transverse to the beam, so it's not electromagnetic field momentum. And these are macroscopic forces, not relativistic forces, so it is not hidden momentum. Just a relevant reminder, mathematically, physics is perfectly comfortable with the idea that momentum need not be conserved, as long as the Lagrangian has a translational variance. Now, of course, I'm going to argue that this constitutes that case, that any free space potential field not associated with a second mass that does work on a target mass constitutes a case where the Lagrangian is not translationally symmetric, that the Lagrangian is translationally variant. In this case, the laser provides the potential field, and the work done is not path independent. This is a little out of context, but a relevant reminder that there are cases where our ordinary intuitions can be quite wrong. So let's talk about the magnitude of the forces. For a 10 milliwatt laser beam with a 5 millimeter beam diameter on a 3 micron particle, we get on the order of 10 piconewtons. But we can scale that up. Let's say that instead of using a 3 micron particle, we use a 3 micron by 3 millimeter wire. That would increase the force we see by about 3 orders of magnitude and give us in the 10 nanonewton range. But we can use a multiplicity of wires. Let's say we have a 3 millimeter by 3 millimeter two-dimensional array. We'd get another 3 orders of magnitude. That would put us in the 10 micronewton range. Now let's crank up the power. We were using only 10 milliwatts. If we use a 1 watt laser with the same arrangement, now we're manifesting forces in the 1 millinewton per watt range. Now, of course, we can explore a 3-dimensional array of these wires, where each 2-dimensional array is separated by half the wavelength of the light. In the ideal case, we might crank it up to 1 newton per watt of laser power, but we can expect some beam quality degradation along the optical path, so maybe we could get it up to 10 millinewtons per watt. Whether that seems practical or not, we'd like to mention take-home number 2. We should be looking for and discussing cases where the Lagrangian has a translational variance, and exploring circumstances where we can use that to our advantage, particularly in space-based propulsion applications. So, in summary, we have noted that momentum is only conserved in the case that the Lagrangian is translationally invariant. This is from Noether's theorem in 1918. We have discussed one case where linear mechanical momentum is not conserved. We have noted how linear mechanical momentum can be accumulated when a dipole is generated and an electromagnetic field gradient acts upon the induced dipole to generate a Lorentz force, the case of optical trapping. We have argued that the microscopic forces active in optical trapping can be scaled up to provide a practical tool for space-based propulsion. And with a bit of practice and ingenuity, I'd still keep my fingers crossed for that 1 newton per watt range. Lastly, we have suggested that we should be looking for and discussing cases where the Lagrangian has a translational variance. Conservation of momentum is a fundamental limitation to our operations in space, and physics tells us that is not necessary. In closing, I'd like to leave you with just a few thoughts, a few quotes from our esteemed Mr. Feynman. One of my favorites is, "If you thought science was certain, well, that was just an error on your part." Another one I found recently is, "We have found it to be paramount importance that in order to progress, We must recognize our ignorance and leave room for doubt. And finally, scientific knowledge is a body of statements of varying degrees of certainty. Some most unsure, some nearly sure, but none absolutely certain. So with that, I'd like to ask a question. Are we certain that we need to conserve momentum? Thank you for your attention.